Hello everyone, we will now discuss an interesting and important topic, especially from engineering services point of view, that is Fermi level in N-type materials. The Fermi level in N-type materials, first of all let us draw the energy level diagram. This is the valence band, this is the conduction band. This is the lowest level of conduction band, this is the highest level of valence band, that is energy E. We will see the Fermi level in case of the N-type materials. For the concentration, I will start the topic, the concentration of electrons in conduction band is given by, remember this expression, I have derived this expression in case of Fermi level in intrinsic semiconductors. This is where I discussed, you can just see that video. So the concentration of electrons in conduction band is equal to N equal to Nc e raised to power minus Ec minus Ef by Kt. That is the expression of concentration of, this is Nc, the concentration of electrons in conduction band. This is very important expression, you should remember. I repeat, this is very important expression. So now for N-type materials, remember this, the concentration of electrons is almost same as the donor concentration. We have seen this in case of semiconductors, but at normal temperature. Now what I have, Nd, that is donor concentration, is equal to Nc e raised to power minus Ec minus Ef by Kt. That is what you have. Let us see it further. This gives what? Minus Ec plus Ef is equal to Kt natural log ln Nd by Nc. That is what you have. Or you can rewrite it like Ef equal to Ec plus Kt ln Nd by Nc. I will rewrite it like this, a slight modification in this expression, that is what, Ef is equal to Ec minus Kt ln Nc by Nd. Remember, the donor concentration is a variable quantity, you can control the concentration, but this Nc, that is density of states in conduction band, is function of effective mass of electron and temperature. This is what you have seen. I repeat, this Nc is equal to 2 into 2 pi effective mass of electron Kt by h square power 3 by 2. That is nothing but Nc. Nc is called density of states. I repeat, Nc is what? Density of states in conduction band. That is known as Nc. And for that you need to see my Fermi level topic. Now this is very important expression, you should remember always if you want to handle, this is K into T. This is very important topic if you want to handle the questions on the Fermi level in case of N-type semiconductors. Interesting part here is Fermi level is function of two things here, the function of temperature and the function of donor concentration and effective mass. So depending upon the temperature, this will be changing. Let us see how. First case, case 1. I will discuss case 1. First of all, if you see this expression, I will say, remember, in case of intrinsic semiconductors, that was Fermi level at the center of the energy gap. I'll rewrite that is EF intrinsic. That is intrinsic Fermi level. That is Fermi level intrinsic. Fine. Now in this case, in case of metals, the Fermi level is not fixed. Fermi level is, in case of n-type semiconductors, the Fermi level is not fixed. Let us see how it goes. The Fermi level EC minus EF, I am assuming this is less than this, so here Fermi level is close to the conduction band. The Fermi level in case of n-type semiconductors is close to the conduction band. I'll discuss two cases one by one. Case 1, effect of temperature. Effect of temperature. Let us see how it goes. See the temperature. Temperature is here. Temperature is here. If you increase the temperature, this will increase. That means this will increase and this will increase. That means density of states in the conduction band will increase with temperature, and this factor will increase. That means this factor will increase, and if this increases, this factor will decrease. That means Fermi level will decrease, means it comes downward. So as temperature increases, Fermi level EF shifts towards what? Towards the intrinsic level. The Fermi level shifts towards what? Center of energy gap, or you can say towards what? Intrinsic Fermi level. It means material tries to behave like intrinsic semiconductors if you increase the temperature. This is important concept here. And if you decrease the temperature, Fermi level will shift upward. You can see this. If you decrease this, this will decrease, this will decrease, this will increase. So as temperature increases, Fermi level increases. That is the important observation. There are a lot of objective type questions in engineering services prelims on this concept. So try to remember this. You don't have numericals in engineering services prelims, you have the theoretical concepts, and these are the concepts for prelims. I repeat, if you see my all the videos, I guarantee you will be able to handle 9 questions out of 10 in engineering services prelims. So this is what you have. Now case 2. Case 2 is what? Case 2 is effect of what? Effect of donor concentration. If you see the donor concentration, that is what? ND. Let us see the donor concentration. If you increase the donor concentration here, that is ND is increase, so this will decrease. If this is decrease, so this will increase. Why? Because this is minus, you are subtracting, so this, if this is decreasing, this will increase. So as the donor concentration increases, Fermi level will also increase. That means if you increase the donor concentration, Fermi level shifts towards the conduction band. So that is important. So therefore Fermi level shifts towards conduction band if donor concentration is increased. This is important note, this is important question, this is very important question. You have a lot of questions here. Now there are certain points to be remembered. This is case 2. Here there are 3 points under case 2 only. I will discuss one by one. Let us see the points. 3 points here. See this. A is what? A is what? If ND is equal to NC, if the donor concentration is same as density of states in the conduction band, and D is equal to NC. So this is log 1, and log 1 is what? 0. So Fermi level is lying at the lowest level of the conduction band. Then this is sub case of 2, B. If ND is less than NC, donor concentration is less than the density of states in the conduction band. This is less, this is more, so this will become more than unity, so log will be positive, this will be positive, so Fermi level will be less than the lowest energy level of the conduction band. Third case is very important. You have again question on this. If donor concentration becomes more than the density of states in the conduction band, the Fermi level is more than EC, and that is the point. When Fermi level is more than EC, that means it enters into the conduction band, and that is a very interesting phenomena. So when Fermi level enters here, this is your Fermi level. In which case, when ND is more than NC, donor concentration is more than the density of states in the conduction band. So that is very important point. When, I'll repeat, when ND is greater than NC, donor concentration is high. This is called what? Heavily doped N-type semiconductor. So when your donor concentration is high, then Fermi level enters into the conduction band. That is what you have. Now here, such semiconductor, such type of semiconductor is called, remember this, that is called degenerate. That is called degenerate semiconductor. So I hope you understand the concept. When the donor concentration is high, Fermi level enters into the conduction band, then that state of the semiconductor is called degenerate semiconductor. We know when the Fermi level is what? That is basically the level at which the probability of occupying that state was what? 50%, but here electrons are lying in the conduction band, and all the electrons will be, most of the electrons will be lying in this. Why? Because electrons lie in the conduction band above this, and this is high concentration zone. Here it is high concentration. In case of what? In case of degenerate semiconductor. Degenerate semiconductor is basically the semiconductor where all the charge carriers lie below the Fermi level. That is the basic definition in general. So now there are two important concepts. You should remember this. Till now we have discussed the effect of temperature, effect of concentration, and then degenerate mode when the Fermi level enters into the conduction band. So now let us see the shift in the Fermi level. Shift in the Fermi level. Shift, I repeat, shift in the Fermi level from what? From intrinsic level. in N-type semiconductors. Let us see how it is shifted. I repeat, just I'll draw the diagram again. Now I'll see, suppose Fermi level is here. Fermi level is at this location. This is Fermi level. You want to see this shift, and the shift is what? EF minus EFI, that is intrinsic level. This is what you want to find. Fermi level in that is a shift in the Fermi level. Now, do you know what is the concentration of electrons? Concentration of electrons is what? N is equal to what? That was Nc into E raised to power EF minus EC by KT. That is what you had. Now, N is what? Nc E raised to power. Now, I will try to relate this with this EFI. So, that is minus EF minus EC. I will add and subtract EFI, minus EFI plus EFI minus EFI by KT. That is what you have. Now, you can write N is equal to Nc E raised to power minus, then what? Minus EFI or EFI minus EC into by KT into E raised to power. Now, you are taking what? EFI, I'll rewrite it like this, minus EC minus EFI by KT. We will see how it comes into what? Now, what I have taken? I am taking EFI and EC both together. That is, but this expression we have, there needs to be a correction. That is EC minus EF in case of N-type semiconductors. So, minus EC minus EF here. Please make a correction here. So, EC minus EF plus EFI minus EFI by KT. So, I will take EFI with this. So, this will be what? This will be equal to EF minus EFI by KT. That is what you have. I am repeating, I am trying to find the relationship between EF and EFI. This is the concentration of electrons. Concentration of electrons in case of N-type semiconductors is given by this. This is what you have seen. So, that was minus EC minus EF by KT. So, what I do, I add and subtract EFI here to just to manipulate. So, that is, I have added EFI, subtracted EFI in this, and if you now instead of EFI, I take EFI with EC here. So, I will take this term with here, and if you take minus sign here, so this will become EF minus EFI. And now, this is equal to, this is something like you are taking intrinsic level EC minus EF, compare with this. If it is Fi, this will become Ni, the intrinsic carrier concentration. So, Ni into E raised to power EF minus EFI by KT, where what is Ni? That is the concentration of electrons at the Fermi level, that is EI, and for energy that is basically the concentration for Fermi, you can say intrinsic level, and that is equal to Nc E raised to power minus EC minus EFI here by KT, that is for intrinsic level, you can say. So, this gives what? EF minus EFI is equal to what? KT ln N upon Ni. That is important expression, and there was one numerical in gate on this expression, that is shifting of the Fermi level from intrinsic level in N-type materials. So, that is what EF minus EI is simply kT ln n upon Ni. Ni is what? Concentration of electrons in conduction band, and this is the concentration of electrons in conduction band only, but that is intrinsic carrier concentration. So that is important expression. I hope you will remember this. There can be numerical in future as well, and that was the concept involved in this particular case. So I will discuss the next topic further, but before that I just wanted to discuss the concept here, the concept of Fermi level in case of n-type semiconductors. So I just wanted to discuss the numerical which has appeared on this shift of the Fermi level. The question was, I'll take just few seconds. The question was, if you, on this particular concept, that was shift of the, that was on p-type semiconductor. So I will take that particular question when I discuss the concentration of holes. So next topic I'll talk about is the Fermi level in case of p-type semiconductors.